Well, the mobile charge carries the current in a MOSFET. In the last lecture, we talked about how the mobile charge is related to the band bending or the surface potential. In this lecture, we want to relate the mobile charge to the gate voltage that produced that band bending. So again, current is charge times velocity. We're discussing the mobile part of that charge, which carries the current. We now understand how that mobile charge varies with surface potential, and in this lecture, we'll relate it to the gate voltage, and we will find that there is a very simple relation between the mobile charge and the gate voltage. Okay, let's begin by looking at the subthreshold charge versus gate voltage. Remember, below threshold, there are mobile carriers. They carry the leakage current, so we're going to try to relate the mobile charge density below threshold to the gate voltage. We have this exact relation between gate voltage and charge in the semiconductor. We also have this approximate relation between gate voltage and charge in the semiconductor. It's this approximate relation that we're going to use now in this lecture. So we'll begin with the expression for the mobile charge as a function of surface potential that we developed in the previous lecture. We're below threshold, so we'll use our depletion layer theory for the surface electric field. And we can recognize that dielectric constant of the semiconductor divided by the depletion depth in the semiconductor, that's the depletion capacitance in farads per square centimeter. So we can write the electric field in terms of the depletion capacitance. We can also recognize then that this parameter M in our simple two-capacitor model is related to the depletion capacitance. So we can solve for the depletion capacitance in terms of that parameter M. We can put that back in the expression for the electric field, and then we can put that expression into the mobile charge. And this is what we end up with. You might wonder, why did we go through all those steps and rewrite the electric field this way? We do it this way because the parameter M is a parameter that we can deduce from measured IV characteristics relatively easy. So it's a convenient way to get a handle on the parameter that we need. So we have our charge, we have our electric field, we have a parameter M. We recall that NB is Ni squared over Na, the electron concentration in the bulk. We put all of that together, and we have our expression for the mobile charge below threshold. Okay, now, we're trying to relate this to the gate voltage. We're using our approximate two-capacitor model to say that the surface potential is some fraction of the gate voltage. Also recall that this key parameter psi sub b, which tells us how much we have to bend the bands to invert the semiconductor, you can easily show from that relation that Ni over Na quantity squared is e to the minus 2 psi b over kT. So stop and prove that to yourself if you don't see it immediately. Now 2 psi b is the potential in the semiconductor. What gate voltage does it take to produce that potential? Well, that's the threshold voltage. And our relation here says that the surface potential is gate voltage divided by this parameter M. So when the surface potential is 2 psi b, we call that gate voltage the threshold voltage divided by M. Okay. Now that allows us then to go back to this equation above it and write Ni over Na squared as e to the minus q threshold voltage over mkt. Okay, so we're almost done. We can take the expression for the surface potential and we can put it in this exponential, and now we've got the gate voltage there. We can take our expression for Ni over Na squared and we can put it in the expression there, and now we've got the threshold voltage in this expression. And when we get all done with that algebra, this is the result we get. This is the mobile charge per square centimeter in the semiconductor when the gate voltage is below the threshold voltage. Okay, so it's small, but it carries a leakage current that is important these days. The takeaway message from all of this now is that the mobile charge as a function of gate voltage below threshold varies as e to the minus gate voltage minus threshold voltage over mkt. right? That's an important relation. It's in a big red box because we should try to remember that. The mobile charge versus gate voltage varies exponentially below threshold. All right, what about above threshold? Above threshold is when the transistor is on, carrying the currents that we want to flow. Well, we have our relation between gate voltage and charge. In general, if we're above the threshold voltage, we will have depletion charge, and we will have mobile electron inversion charge. And the bands will be bent by some amount that is greater, a little bit greater than 2 psi b. The threshold occurs at the point where we just bend the bands by 2 psi b, and at that point, we don't have very much mobile charge. We're dominated by the depletion charge. So that's our expression for VT. All right, let's see what we can do with that. So this is our gate voltage expression above threshold. If we put 2 psi b in there, then we have to evaluate the depletion charge at 2 psi b as well. If we subtract VT, you'll see that many of these terms subtract. And now the depletion charge at 2 psi b appears in the threshold voltage. When we're above threshold voltage, it's the depletion charge at 2 psi b plus a little bit. Remember, it's hard to bend the bands above threshold. And the depletion charge only varies slowly with surface potential, as the square root of surface potential. So when we do this subtraction, those depletion charge terms are going to subtract out, approximately. When we get all done, we get a really simple result. Charge is capacitance times voltage. In this case, it's negative charge because these are electrons that we're talking about. And it's only part of the charge. It's the mobile charge. So we can't use the entire gate voltage. It's the amount that the gate voltage is above the threshold voltage, because that's when this mobile charge dominates. So we have a very simple expression. Mobile charge is equal to minus Cox Vg minus Vt. Also in a big red box because we want to remember that. We've used it many times before in this course, and now we see where it comes from. So we've done our mobile charge versus gate voltage. The takeaways are that the mobile charge varies exponentially as e to the Vg minus Vt over mkt below threshold. And the mobile charge well above threshold varies as minus Cox Vg minus Vt. So exponentially with gate voltage below threshold, linearly with gate voltage above threshold. Now, this is not quite correct, and we should explain why, because the correction is important in modern transistors. This is the correct result. And the correct result, we don't have the oxide capacitance there. We have the gate capacitance measured in strong inversion conditions. That turns out to be generally a little bit less than the oxide capacitance. Enough less that people worry about it these days. And this occurs when we're under on-state conditions, when the gate voltage is well above the threshold voltage. So let's see if we can figure out why that happens. Why is the capacitance a little bit less? So I have to remind you that capacitance is charge divided by voltage. When we have a nonlinear capacitance, it's the derivative of charge with respect to voltage. And to get a positive capacitance, we have a negative sign out front there because the charge in the semiconductor is negative under inversion conditions. So now let's look below threshold first. We have a metal gate, we have an insulator, we have a depletion layer. So we have a capacitance, a total capacitance that is the sum of two capacitors. The first due to the oxide and the second due to the semiconductor, to the depletion layer in the semiconductor. That's C sub S, the semiconductor capacitance. Okay, so under depletion conditions, the capacitance that we measure on the gate is significantly smaller than the oxide capacitor because of this second capacitor in series with it. Now, well above threshold in strong inversion, at first glance we would say that, well, under strong inversion, we have a highly conductive layer of electrons right below the oxide. So it's like we have two metallic plates surrounding the oxide layer. The capacitance of this system should be just the capacitance of the oxide layer. Well, turns out that's not quite right. There is some capacitance associated with this inversion layer. You could think of this capacitance qualitatively as the dielectric constant of silicon divided by the thickness of the inversion layer. The thickness of the inversion layer is very small, it's very thin, so this is a very big capacitor. Years ago it was so big that when we put it in series with the oxide capacitor, it had no effect. But these days the oxide capacitance has gotten so big that it's important to include the semiconductor capacitance as well. And the result is that when we measure the capacitance and strong inversion, the inversion layer is not quite a metallic plate. It has some capacitance, so the capacitance that we measure under strong inversion conditions is a little bit less than the oxide capacitance. I will refer to that as C inversion, the capacitance measured on the gate under strong inversion conditions. So here's what we have. We have our expression below threshold. Mobile charge varies exponentially with Vg minus Vt. We have our expression above threshold. Mobile charge varies linearly with Vg minus Vt, but the capacitance is this inversion capacitance, which is a little less than the oxide capacitance. Now, there are a couple of terms that I just want to mention here quickly. You'll hear people refer to something called the equivalent oxide thickness. I've been mainly assuming that we're using silicon dioxide for these MOS systems. And for most of the history of MOSFETs, that was the insulator for MOS systems. More recently, semiconductor engineers have gone to higher dielectric constant materials, so-called high K gate insulators. So there will be some dielectric constant and some thickness, and that dielectric constant will be significantly larger than the dielectric constant of SiO2. The capacitance is just dielectric constant divided by thickness of that insulating layer. But people like to reference it back to SiO2 and say that capacitance is equivalent to how many nanometers of SiO2. That's called the equivalent oxide thickness. And you can just set these two expressions equal, and you can see that the equivalent oxide thickness is just the ratio of the dielectric constant of silicon dioxide, about 3.9 or 4, to the dielectric constant of this insulating layer that we're using, times the thickness of the oxide. So what we'll find is that a relatively thick insulating layer will be equivalent from a capacitance perspective to a very thin SiO2 layer. So it's electrically thin for capacitance, but it's physically thin, and that suppresses quantum mechanical tunneling and makes sure that electrons from the gate can't tunnel through the oxide and give us a gate leakage current. So we get high capacitance, as high as we could get with a very thin SiO2 layer, but we couldn't use those thin SiO2 layers because they would be too leaky. That's why high K gate dielectrics are used, and this is how equivalent oxide thickness is defined. There is another term that you will encounter. It's called capacitance equivalent thickness. So remember we said that the capacitance measured under inversion conditions is the series capacitance of the oxide and the semiconductor capacitance, and it ends up being a little bit less than the oxide capacitance. The equivalent oxide thickness, which we've just discussed, is about the oxide part of this. The capacitance equivalent thickness is about the total measured capacitance under strong inversion conditions. The total capacitance is the series combination of those two capacitors, the semiconductor capacitance in inversion, and the oxide capacitance, and that's a little less than Cox. And we simply equate that measured capacitance, again, referencing back to SiO2, we equate that to the dielectric constant of oxide divided by some capacitance equivalent thickness. So this is the equivalent thickness of SiO2 that would give us the measured capacitance of this more complex system. All right, two quick examples to show you how this works out. Let's say we have a layer of hafnium dioxide, which has a high dielectric constant. And we would like to achieve a capacitance that we could get with 0.9 nanometers of silicon dioxide. But we can't use 0.9 nanometers of silicon dioxide because it would be too leaky. Electrons would quantum mechanically tunnel through it. Well, if we ask what's the equivalent oxide thickness for this system, we simply use our formula. It's a ratio of dielectric constants. We plug numbers in, and we see that with 5.8 nanometers of hafnium dioxide, much, much thicker than the 0.9 nanometers of SiO2 we would need for the same capacitance, we can achieve the same capacitance. But that's a thick enough layer that we can suppress the tunneling. Okay. All right. A second question. Let's say the measured capacitance on the gate under strong inversion conditions is 3 microfarads per square centimeter. What is the capacitance equivalent thickness? So this measured capacitance, this includes some insulating layer, might be a high K layer. It includes the capacitance of the inversion layer, which is finite. But what thickness of SiO2 is that equivalent to if we had 2 metal plates surrounding silicon dioxide? Well, we simply equate that measured capacitance to the dielectric constant of oxide divided by this capacitance equivalent thickness, and we solve for the capacitance equivalent thickness, and we deduce that 1.2 nanometers of silicon dioxide would give us the capacitance that's measured under these conditions. All right, two terms. Let's try to keep them straight: equivalent oxide thickness and capacitance equivalent thickness. So to summarize everything now, if we have a fully depleted ultra-thin body structure, below threshold, the inversion layer charge or mobile electron charge varies exponentially with Vg minus Vt over Kt. For the bulk structure, below threshold, the mobile electron charge varies exponentially as Vg minus Vt over mkt, and m is greater than 1. So for the ultra-thin body structure, m is equal to 1. For the bulk structure, m is a little bit bigger than 1. So this is a significant advantage we'll see later on for the ultra-thin body structures. Above threshold, both systems behave the same. The mobile charge is the total gate capacitance times Vg minus Vt. Varies linearly with gate voltage. All right, we have derived this expression that we used way back in the beginning of the course. Mobile charge is minus oxide capacitance times Vg minus Vt, and we've learned it's not quite the oxide capacitance, but it's close. Now we're ready to move on. In the next lecture, we need to look at 2D electrostatics. We've been looking at 1D electrostatics. We've been drawing band diagrams through the depth of the semiconductor as we bend the bands from the surface into the depths or through the ultra-thin body structures. But MOSFETs are 2 or 3-dimensional structures. There are electrostatic fields in 2 and 3 dimensions. MOSFETs are very small. These 2 and 3-dimensional fields have become quite important. How do they affect the performance of MOSFETs? That's what we'll discuss in the next lecture.